Hello, everyone. Um, I had a number of people who's working on this Kirchhoff's law worksheet, and they got to this problem that I've drawn up here. I do have a whiteboard now. That's excellent, but I don't have necessarily the greatest of setups. You can probably see that the lights, when I turn the lights on, do weird things. So that's okay. Um, I'll show you my cat Francis here in a minute. Uh, what I want to do is get you started. I sent y'all a little bit of information about solving linear equations. At least one person I saw used the stuff they were doing in linear algebra, and that's great. And basically, what I want to practice is setting it up because I think once you know what the currents are, then it becomes like the other problems. You can go through and apply Ohm's law to a particular resistor and it works, and you'll get the voltage across it. All right, so we have a circuit like this, and uh, we wanted to define where the currents go. And when I ended the last video on this, what I said was that this current going through these resistors is what I'll call I2. And I saw other people do different things, and that's fine. All right, some people said it went upwards. Some people call that I1, or they called it I3 or what, doesn't matter. As long as you're clear labeling that, then that's what we go with. So this is I2. You try to fix things and they don't quite work out. There's I2. And then we're going to call this current goes this way I1, and the current goes this way I3. And so that gets us an equation is I1 equals I2 plus I3. And that's all well and good. Now, that was the first step, is just identifying where the currents go. The second step is identifying on all these parts. All right, when we say put in the pluses and the minuses, what we're saying is we want to know if we compare 2 points on the circuit, which one has the higher potential and which one has the lower. For the batteries, that's easy, right? For the 6 volt, it's plus and minus. And for the 20 volt, it's plus and minus. All right, the long wire always has the higher potential on the battery symbol. All right, so what this says is if we say this wire at the bottom is 0 volts, this wire right here has to be 20 volts. And this wire right here has to be 6 volts. That's the definition of how a battery works. If it's a 20-volt battery, it has 20 volts across it. Now, of course, as batteries get used, that changes, but, nominally, a 20-volt battery is 20 volts. Now, we don't know anything about these points or this point yet. And that's where we end up when we say what is the voltage across each resistor. We're comparing, say, this point and that point to get the number on the 15 ohm resistor. Or we compare this point and that point to get the number on the 60 ohm. And so you may get numbers that are slightly different, and that's okay. All right, you may get negative numbers, and that means, well, the current probably flows the other direction. All right, so if the current flows, it always flows from positive to negative. So the way we've laid this out, it flows, here's a positive and here's a negative, and here's a positive and there's a negative. All right, I1 flows from the positive to the negative here, and I3 flows from positive to negative there. All right, so this has to be higher potential than this, and that kind of makes sense, right? We start here at 20 volts. This has to be lower than 20 volts. So this has to be lower than 20, but it has to be higher than 6. So it's between 20 and 6. Right, and then this is 6 volts and this is 0 volts. And then the way it splits here, we have a plus and a minus and a plus and a minus there. Right? So that's the way it looks there. And now we've already written one equation up for going around the loop in this way and having, I'm noticing that I don't have a lot of colors here. I have purple. Let's go purple. So I'm going to draw in the loops that I'm going to do in these colors. And there's 3 loops. One is the left loop that encloses the 20 volt and the 30 ohm and 60 ohm and 15 ohm elements. There's the right loop that encloses 16, 15, and 25 and the 6 volts. And then there's the outer loop, which ignores this stuff in the middle and does 20 volts, 30 ohms, 25 ohms, and 6 volts. Now, those are overdetermined. If I take the left loop equation that I get and add it to the right loop equation, I should get the outer loop equation. So that's a check. If we find all 3 equations and they're consistent, then the left plus the right equals the outer. Now, that's true for this. You can get some weirder geometries, and I'll try to show you one here in a little bit. Maybe not this video, but you can get some weirder stuff where you have to kind of go through and do multiple equations. But this is the hardest I want to deal with, because if there's 3 loops, that means there's 4 equations. If I put in 10 loops, there's 11 equations. I'm not going to ask you to solve a system of 11 equations. Just so you're aware. So what we're going to do is take the loop that goes this way around, take the left loop, and we're going to start at this corner. And what we do is we go from negative to positive. And there's 2 ways to do this. What I would do is, if we go from negative to positive, you get a positive number. And if you go from positive to negative, you get a negative number. All right? So what we would get is positive 20 volts. And that is a horrible thing I'm writing, because I'm writing at arm's length. We get 20 volts. And then we go up. Now we're going positive to negative. Right? So you can think these things are oriented. I can either pick the second symbol, which will be positive, negative, 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 or I can pick the first symbol, which will be negative, positive, positive, positive. You get the same signs either way, eventually, right? Because we're going to write this out. We're going to end up back at this point, and around the loop it equals 0. So we'll have 20 volts, and we took positive. So we went negative to positive. Then we go positive to negative, so it's minus 30 ohms times I1. And what this is this is the potential across that resistor. This is V. But we don't know what V is, and we're applying Ohm's law. And Ohm's law is V is I times R. So we're doing I1 times 30 ohms. And then we're going to go across these, and it's going to be minus 60 ohms times I2, positive to negative again, and then positive to negative here is minus 15 ohms times I2. And this equals 0. So that's great. We got the left equation. That works. Now we're going to get the right equation. And we're going to start at this point and go around a loop like that. And so there, we're going to go this way around. And it might make sense to go the other way around. It should not matter. We're going to use the same convention. So we go negative to positive. That's a positive. So we'll have 15 ohms times I2. And then we go negative to positive plus 60 ohms times I2. And then we fall down this other side. So minus 25 I3 and minus 6 volts is 0. And at that point, that's enough. You don't need to do any more if this is right. The idea is that you have 3 equations. This one uses all 3 variables. You have one that just uses I1 and I2, one that just uses I2 and I3. But you have 3 equations and 3 unknowns. It's solvable. Now I am going to do the outer equation. Right, so it's going to start in this corner. It's going to go all the way around the outside. I'm not going to draw it here because the drawing is getting a bit busy. But this fourth equation will be 20 volts, negative to positive again. And then we go positive to negative on everything else. So minus 30 ohms I1, minus 25 ohms I3. There should be an ohms here. And minus 6 volts. That equals 0. Right? We go along the loop. We see 20 volts first. Then we see the voltage on the 30 ohm resistor. Then we see the voltage on the 25 ohm resistor. Then we see the 6 volts, and that's falling. It's positive to negative. And we see nothing else there. And if I'm careful, I'll go back and I'll show you that these terms here match the two terms above it in the red equation. And these terms match the terms above it in the purple equation. And if we take the purple and the red equation and add them, these other terms cancel out. We cancel the 60 ohm times I2. We cancel the 15 ohms times I2. And so they go away. And so this is consistent. So what I'm going to do is pause for a moment, erase the drawing, and rewrite these equations. Okay, so we have these equations, and all we're going to do is simplify them. We know what the units are going to be. We're using ohms and we're using volts. So we're going to get amps out of this. And we're going to rewrite the equations, and we're going to write them in such a way that we can substitute one variable in for another. Right? So I'm going to write up here and above, I'm going to write, oops, that's a little too high. I need to put barriers on this. I1 minus I2 minus I3 is 0. Right? That's just rewriting this so all the terms are on one side. We're going to write the purple equation, and we're going to write in terms of I1 and I2. So we'll have 30 I1, and then we add these two because they're both I2, and there's a minus sign here. I'm going to hold off the minus sign for a minute. So we'll have plus 75 I2. We'll have no I3. And so we're going to subtract 20 over. So all these should be negative, and 20 should be negative. And so those negatives cancel out. So it's just keeping track of things, right? There are negatives in here, and then we cancel them all out. Right? That's where they went. And in the red equation, and we're not going to work with this fourth equation because it's too many. We're going to write this one out. And so the I2s will add up. So we'll have 75 I2. We won't have an I1. And we'll have minus 25 I3 equals 6. The 6 goes over to the right. I'm going to pause again. Okay, so what we have here, we have a system of equations. We have 3 equations and 3 unknowns. And I do things the mechanical way. I go through and solve longhand. However, this is a sort of thing where if you have a linear, if you have a set of linear equations like this, you can write this as the stuff you learn in linear algebra. If you're taking only differential equations, then maybe you know this if you saw the stuff in algebra 2. I don't know. but it's writing this out basically so you can put it in a calculator. But I'm going to do it the longhand version. All right. You've seen this in linear algebra. What I've done is I have a matrix on the left side, and that equals a vector on the right side. And I'm looking for the vector I1, I2, I3 that that makes this system work out. Right. I'm trying to solve for one vector multiplied by this matrix that gives me the answers over here. If you're not in that class, don't worry about it. You'll take it some other time. So the trick here is we're going to solve, right? We're going to pick an equation and we're going to try to solve everything in terms of a single variable, right? And what we want to do is kind of isolate out things that we don't need, right? Is the equation at the top here, we can write in terms of I3, and that will let us get rid of this I3 down here. What we'll have is I3 equals I1 minus I2, right? And that's just pulling this over to the right and then flipping it around. Now that means we can plug it in to this equation. So we have 75 I2 minus 25 I1 plus 25 I2 is 6. What I've done is I've taken this, plugged it in for I3. And now I have this other equation, 30 I1 plus 75 I2. Have I done that right? 30 I1 plus 75 I2 equals 20. Right. Now, this one has two terms in terms of I2. So what I'm going to do is get rid of this one and put it in up here. It's actually 100. 100 I2 minus 25 I1 is 6. Now it's a system of two equations and two unknowns. And the idea is that once we get I1 and I2, we can plug back in to get I3. So this is the thing we're trying to solve now. So pause again. This is actually like a 2.5 by 4 foot board. If you want one of these for yourself, like if you're in college and you want a big marker, what you do is you go to Lowe's, you go to Home Depot, and you go to the paneling section, which is where the lumber is. And you look for what's called marker board or wainscoting board. This is the stuff that goes along like kitchen walls, where you want something that's very easy to wipe off, and you want it to you want to make it look clean, right? So where you have in like dining rooms, you want the chairs not to hit the wall above the back of the chair, right? You want the below that to be a nice solid color so you don't see scuff marks. And above that, you want it to be white because you want it to look kind of antiseptic. You want the dining area to be clean. Right, so that's if you ever have to design a Denny's somewhere. Don't do that, design Waffle Houses. So we're going to solve this equation in the box. And a lot of people I saw like tried to simplify out things, right? You would have something like I2 plus I2 plus 1/4 I1 is 6. I don't like doing that. I mean, it's okay. You can do it, and sometimes that's the easiest thing to do. But what I like to do is get these equations. Have I made a mistake somewhere? No, I haven't. What I've done is on my notes off to the side, I have a common minus sign everywhere in here. So I've done it a slightly different way, and that's okay. So the idea is what we're going to do is write this, and we're going to take this equation here, and we're going to multiply it by 4 over 3. Right? And so the idea is this will get a term here that's 100. And so what we'll get is 40. Again, I'm too high. Let me draw a line right here. There we go. So no, not to right above that. So 40 I1 plus 100, right? 75 times 4 is 300, divided by 3 is 100. I2 equals, and then 20 times 4 is 80 over 3. Kind of can't deal with that any other way. Now we're going to have another equation, which is this one. That's going to be minus 25 I1 plus 100 I2. And that equals 6. And I'm going to put this in common denominator with this. So it's going to be 18 over 3. And the reason I did that was so that I can subtract these two equations. Right? Because what I want to do is get rid of the I2. So when I subtract them, the right side is going to be 62 over 3, which is 0.318. I know that's 0.318 amps. Nope, I've done that wrong. Just leave it as 62 over 3. Hint, that's what the answer for I1 is. The other side, it's going to be 40 minus 25 is 65 I1. And these cancel out because we're subtracting them. It goes away. And so this leaves you with I1 is going to be 62 over 65 divided by 3 is 0.3. Let me write that out. 1 over 65 times 62 over 3, and that is 0.318 amps. That's I1. Now, briefly, I'm going to hold up, so you have that in front of you. I'm going to hold up the original thing there. There's a big current flowing out of the 20-volt battery, and we say it splits up. So we expect I2 and I3 to be smaller than this. All right. So as we're going through this problem, you're going to get the other two things, and they're going to be numbers smaller than 0.32 amps. And we have one more thing, is that we know I1 goes through the 30 ohm resistor. So for this 30 ohm resistor, we know V is I times R. And I here is the current that goes through it, which is I1. So it's going to be 0.318 amps times 30 ohms, and that is 9.54 volts. And that's what we want. That seems like that's, I mean, it's not too big. What I saw some people do when they worked their equations out, they got something like I1 was 1.5 amps and I2 was 2 amps, something like that. And that resulted in calculating these potentials to be 30 or 40 volts across these resistors. And that's there's no thing in the circuit that could generate it. Right? If you remember, the batteries were 6 and 20 volts. So you want to make sure that the numbers kind of make sense as we go along. A 20-volt battery could generate this voltage drop across that 30 ohm resistor. And across the other ones, you need to make sure that they make sense. Right? I2 is going to be smaller, so you're not going to get something weird like 18 volts across the 60 ohm resistor. You're going to get something smaller. Right? But it needs to make some sense. If you do Ohm's law with the current that goes through that resistor, you'll get a an appropriate potential difference. So that's where I'm going to pause. This is just to kind of help you out through that one problem. I want y'all to keep cranking at it. I'm going to do another video where we go through a different example problem, just a completely different one, so you have something else. And we'll see how this goes. All right, let's see if I can stop this. Oh, wait, I promised y'all Francis. She's asleep over here. Give me a moment. You're also going to see a little bit of my room, which is an office, kind of. There's where I pile all of my junk, my tools, my soldering equipment, and right beside it, the cat food and the cat water. And then there is my baby. I love her so much. She's asleep right now because she can't believe I'm working this late at night. So actually, it's only 11. So, yeah, my sleeping quarters are basically my office as well. Um, I do have other space. Hopefully, I'll get that set up tomorrow, but it's uh, not conducive at the moment. So hopefully, I'll have a big whiteboard and lots of fun stuff to do. Anyway, y'all have a good evening.